All right, let's take a look at an RC integrator. And before we do that, we'll go over a few definitions. So a function. So, if there's a condition that depends on one or more conditions, we say that the condition is a function of one or more of those other conditions, if that makes sense. But using functional notation, Ohm's law can be expressed as f of IR is equal to IR, okay? Which just means that the voltage is a function of the current and the resistance. And then using functional notation, f of R is equal to pi r squared, and you write that instead of the area is equal to pi r squared, okay? So this in functional form is this here, okay? That's all a function is. But a derivative measures the rate of change of a function, and if the function is f of x, its derivative, d over dx, f of x, gives a slope of the function at any point, okay? Now, an integral is a reverse of differentiation. It's the antiderivative, or the indefinite integral. And the integral of a function f of x gives a function whose derivative is f of x expressed down here, this formula down here. And so capital F of x is the antiderivative, okay? Now this plus c, all that is, c is the constant of integration. Now a derivative of any constant is 0. So if there was a constant present, you just have to add it back in. We don't have to worry about that. But so if you have d over dx, c, that's going to be equal to 0. The constant c doesn't change with respect to x, okay? Its rate of change is 0, so that's going to be 0 there. And that's the only reason we add that in there. So what we're going to do is we're going to take the integral of a sine wave, okay? And then we're going to display it on a scope, okay? So to take the integral of the sine wave, you use this here, this integral of sine x dx, and that's going to be equal to minus cosine x plus the c, which we don't care about. Now, to get the phase shift, okay, so the phase angle is going to be equal to minus the cotangent of the angular frequency times RC, okay? So this angular frequency, here it is here, it's just 2 pi radians divided by the time for one cycle, okay? So 2 pi is just 360 degrees, but we use it in radians, and then we divide that by the time. So our frequency divided into 1 gives us this time here, and then if we can rewrite that as this angular frequency is equal to 2 pi times the frequency, okay? So we have we want to calculate the phase shift here. We take our we got to take our the angular frequency times RC, so we take the 2 pi times the we get our angular frequency in rads here, okay? So it's 62,832 radians per second, and then we times that by our RC constant here, which is going to be frequency is 10,000, oh no, 10k resistor, and then our 10 nanofarad capacitor here. And when we calculate out, it comes out to 6.2832. So we take the arctangent of that of 6.283, and it comes out to about minus 81 degrees, okay? So we're going to go over to the scope, and we're going to put the circuit in there, and we're going to put our 10k hertz in here, and then we're going to take our we're going to get our phase shift out on this side off the capacitor over here. And then we want to calculate the phase shift. We do that, the phase angle here is going to be this delta t, which is the time between the two different phases here. I'm taking the one off of V in and then one off of V out here. And then we divide that by the time for one cycle, which is our 10,000 divided into 1, okay? And then we times that by 360 degrees. And so when we do this, that should come out to about 81 degrees, negative 81 degrees, okay? And we'll head over to the scope, and we'll see what happens. All right, here we are at the oscilloscope, and the yellow trace happens to be a derivative. I'm going to integrate it also, but for now we'll take a look at the derivative of it, and we're going to find the phase angle between the two of them. So I got the two cursors there where they both cross the center line, and it happens to be 23.2 microseconds. And then what we do is we take that and we divide that by, or one. We have I don't know if you can see it up in the corner there, but there's it's at 10k hertz, and so we divide that into 1. We get 0.0001. We divide that into our 23 microseconds there, and then we multiply that by 360 degrees, and it comes out to like 82 something. The phase angle is about 82. Now I calculated it at 81 point something, so we're pretty close there. I'm going to go over to the I'm going to switch it up and do the integration of it. And of course, you know, I have the resistor and the capacitors here aren't the values of there, you know, they're 5% or so, so we could be off a little bit. But anyway, we'll switch over to do the integration of it, and we'll see what happens. All right, now we're integrating the sine wave. You can see it's the same phase shift. It's the 23 microseconds, and then we divide that by our 1/10k and times that by 360, and it comes out to 82 phase angle of 82, but it's minus. You can see that the yellow is on the opposite side now. So there we go. We integrated, and we took a differentiated too. So yep. And so anyway, that's how you do a little analog math. And what's nice about it is you can prove the formula works, with the scope by actually viewing the sine waves. So anyway, that's how you integrate a sine wave, or take a derivative of a sine wave. And thank you.